Welcome, everyone. My name is Nathaniel Short, and I'm the chapter leader for Snohomish County Citizens Climate Lobby, which meets every third Monday of the month at 7 p.m. If you too are concerned about climate change and want to know more, consider dropping in on a live informational session given every Wednesday at 8 p.m. Eastern Time, 5 p.m. Pacific by CCL National. I feel very fortunate to be able to host this talk by Dr. James Conca, a fellow Citizens Climate Lobby member and a world-class expert on nuclear waste, recognized also for his depth of knowledge on all forms of energy production. This talk was presented to the Washington State CCL chapters on Tuesday, June 27th at 7 p.m. and is the second of two talks by Dr. Conca, with tonight's session focused on nuclear waste. The first talk was given last Thursday on June 22nd, covering a wide range of energy-related topics, from the geopolitics of energy to the state of energy in Washington State. To find this, simply Google YouTube, The Geopolitics of Energy by Conca. And now a little background on Dr. Conca, or Jim, as he prefers. Jim is a trustee of the Herbert M. Parker Foundation at Washington State University in the Tri-Cities. He's worked on a number of energy issues for 40 years at NASA, Washington State University, New Mexico State University, Los Alamos National Laboratory, Pacific Northwest National Laboratory, and the Lawrence Livermore National Laboratory. He's been an advisor to the DOE, EPA, state and federal regulatory agencies, and to President Obama's Blue Ribbon Commission on America's Nuclear Future from 2010 to 2012. He worked on the Yucca Mountain and WIPP nuclear waste projects for 25 years and was a science contributor to Forbes on energy issues for 10 years. He's also an advisor to the new Washington State Legislature Bipartisan Nuclear Caucus. Conca obtained a PhD in geochemistry from the California Institute of Technology in 1985, a master's in planetary science in 1981, and a bachelor's in geology and biochemistry from Brown University in 1979. And that's why I feel privileged to host Jim here tonight. And with that, I'll hand it over to you, Jim.
Back here to the slide. Okay, so we ended here. So the whole point is to talk about, what happened to our nuclear waste disposal program. It got kind of derailed about 40 years ago, and we have not really recovered. And that's one of the problems. So there are, let me close this up a bit. There are 4 categories of nuclear waste in the United States, a little different than Europe because we have so much defense waste, so much bomb waste, and they don't have very much at all. So the hottest stuff is spent nuclear fuel from a commercial reactor or a weapons reactor, but we don't have any more. We mothballed them. They were all at Hanford and a couple at Savannah River. But that's so spent nuclear fuel. And that's a solid. Pretty much, it looks like this. It's just, uranium oxide and other, solid metal materials. So there's nothing to leak. There's no liquid in it. Then the next category is high-level waste, and that is only bomb waste. Now, this is important. The next two, high-level waste and transuranic waste, are only bomb waste. There's no such thing as high-level commercial waste. All right, there's only high-level bomb waste and transuranic bomb waste. And the high-level waste, like the stuff that's in the tanks at Hanford, or used to be, is this gooey, peanut butter-like textured junk with salt cake on it. I mean, it's really gross, and it's kind of hard to handle. Now, transuranic just is any form. It's debris waste, it's grout, it's sludge, it's whatever it is. And I'll talk about what that is, but it's not. It's from the reprocessing of spent fuel from bomb reactors, weapons reactors, in order to make nuclear weapons, in order to purify plutonium for nuclear weapons. Then there's low-level waste, which is mostly dirt, it turns out, and other, medical stuff and just junk that's not that hot and doesn't fit into either of the other 3 categories. Now, the thing is, deep geologic disposal is required by law for the top 3, for spent nuclear fuel, high-level waste, and transuranic waste. Oops. So I need to give a short nuclear primer. So uranium-235 splits easily, it fissions easily. Uranium-238 does not fission easily. You mine it in an ore just like you mine iron ore, and you have to separate it, smelt it, basically, until you get U3O8, which is yellow cake. Then you have to do some kind of enriching. Natural uranium is only 0.7% uranium-235, and it's almost all 238. Now, a rule of thumb is if it's an odd number mass, like 235 or uranium-233 or plutonium-239, those split easily. If it's an even number nucleus mass, 238 or plutonium-240, or they do not split easily. All right, so keep that in mind. Now, in order to form a sustained nuclear reaction, either controlled or uncontrolled, you need to enrich the amount of 235. So you either enrich it to 4%, it's still mainly 238 for commercial fuel, or if you want a weapon, you need to get it all above, 93.5 or so, 235. It has to all be the element that splits easily. Now, to do that, nowadays, we dissolve the yellow cake up in acid, and we put it in hydrofluoric acid and form uranium hexafluoride gas, and then put that down 30,000 centrifuge tubes until, and then, cascade from one to the other. When you're spinning up, at 20,000 RPM, the slightly heavier uranium-238 goes to the outside, the slightly lighter 235 goes to the inside, and you just cascade that, bleed it down 30,000 centrifuges until you get to the level of enrichment that you want. Now, various new reactor technologies like the SMRs, the pebble bed, other reactors can have higher than 4%. They can't have higher than 20%, because higher than 20% 235 is considered weapons grade, although no one would ever dream of making a weapon with less than 90% 235, because it would mainly be a dud. And your weapons better work if you're going to use them. Okay. So why is this important? Why is this any good? So uranium-235, a neutron comes into hits the nucleus, splits into two unequal parts called fission products, 3 neutrons out and a bit of energy. Okay, so 3 for 1, such a deal. That's why this works. So you have these 2 fission products. They're unequal size. One's about 140 mass and the other's about 90 mass. They can be various things. There's a whole range of particles that come out based on the probability and the speed of the neutron and exactly how it hits the nucleus. But basically, you get two fission products out and 3 neutrons. Now, if you're a bomb, if you're all 235, then those neutrons see more 235, right? Because it's all 235 if you're a bomb. So then they split, and now you're at 9, and then 2781, boom. In a microsecond, you're at a 10 to the 20 neutrons and 10 to the 20 splits. Now, the power of a nuclear bomb has nothing to do with radiation. It has to do with the speed at which these 2 pieces are flying apart. It's a kinetic. It's a bomb. I mean, it's just a big-ass bomb. Okay, so these 2 things are flying apart, some of them even near light speed. So if you have 10 to the 20 of these splits going apart, the pressure and temperature is unimaginable. And that's why a nuclear bomb works. When we talk about nuclear bomb size, we talk about kilotons of TNT equivalent or megatons of TNT equivalent. That means if you put 13,000 tons of TNT in one spot and were able to ignite it all in the same microsecond, you couldn't tell the difference between that and a nuclear bomb. Same mushroom cloud, same devastation, everything, except you wouldn't have a little burst of neutrons at the edge. And so of the 250,000 people who died at Hiroshima and Nagasaki, they died because of the blast. Only 4,000 eventually died from radiation. And that's only because they were standing around the edge of the blast when that pulse of neutrons and high energy gamma came out at that microsecond. It was only that microsecond. All right, there's no fallout from Hiroshima and Nagasaki. There generally is no fallout at all from a nuclear weapon if you detonate it at the right height. And for all the tests we did above ground, there's only one that we messed up on, and that was Bikini Atoll. And that's why that was such a mess, all right, in 1963, I think it was. Because if you, to maximize the blast, and and I'm getting into bombs because most of the waste we have is bomb waste. So when you want to maximize the blast of your bomb, you want the most yield, right? The biggest effect. Then you detonate it at a certain height, and we know exactly what that height is per yield. So in Hiroshima and Nagasaki, it was about 1,500 feet. All right. If you go lower, if you detonate it too low, then the blast is not as big, so your yield is much lower. But then you suck up material into the mushroom cloud, which gets activated in that microsecond, and then that's your fallout. So generally, you have no fallout because we know at what altitude to detonate these bombs, and even the Russians know that. Everyone knows that. All right. Bikini Atoll is weird because we thought it was only going to be 5 megatons, and instead it was 15 megatons, which was the biggest bomb we ever made. And so we screwed up. I mean, we detonated it too low. But that was the only one. All the above ground nuclear tests we did at the Nevada test site, there was no fallout to speak of. The downwinders actually have lower cancer rates than anyone else in the country, which is very funny. So bombs are kind of weird. They're interesting, but yeah, we should have a separate talk on bombs probably. Now, if you're fuel for a reactor, then you're only 4 or 5% depending on the reactor design. So most of when the nucleus splits of uranium-235, those 3 neutrons generally do not see another 235. They see 238 because it's still 95% 238. And so that does not split. Okay, that captures the neutron, turns into uranium-239, which is very unstable, and then quickly beta decays, which means it throws off the nuclear equivalent of an electron, and forms neptunium. I'm sorry, not neptunium. It forms neptunium as an intermediary, and that beta decays and forms plutonium-239. So you are breeding plutonium from uranium-238. So when you hear the term breed, that's what it means. You're breeding another element from a previous element, usually from neutron capture, sometimes alpha decay, whatever, but that's what you're breeding. Now, there's different breeding pathways that give different things, like, again, neptunium, 95% of the time it beta decays to plutonium-239, but 5% of the time it decays it to something else. So that's how you form americium and all of the periodic, the last row of the periodic table, the actinides. You do that by breeding, basically, and decay. So you're breeding plutonium from uranium-238. Now, in a commercial reactor, after 2 years, you bred so much plutonium and it burns right away. I mean, plutonium splits much easier in 238. That's why you want it in your bombs. So plutonium-239, after 2 years in a reactor, is producing more power than the original 238. All right. Now, and that's fine because it's burning, it's breeding and burning. Okay. Now, after 6 years, these fission products have built up to the point that they start scarfing up all the neutrons and the thing fizzles out. It's not spent, it's not used up, it's got too much junk in it. So you can recycle it, reprocess it, get more fuel and make MOX fuel. That's a combination of uranium and plutonium left. And that's new fuel. And the French do that, the Japanese do that, the English do that. And that's fine. Or you can just set it aside, let it cool off, and either burn it in Bill Gates' fast reactor when it gets going, or that's what fast reactors do, and get 10 times the amount of energy out of the same waste, or you can just throw it away if you don't want it. That's fine. Because we have so much uranium, it's not funny. But I prefer putting it aside and burning it in future reactors. Now, that's a commercial reactor. If you're a weapons reactor, you cannot let the fuel stay in the reactor more than 6 months. Because after 6 months, you start breeding in neutron poisons like plutonium-240 that doesn't split and cannot be separated. And so you can't use commercials, or you can't use fuel that's been in the reactor more than 6 months. So reactor fuel's in there for 6 years, and you bred in so much plutonium poisons that you cannot neutron poisons it, you cannot make a weapon out of that. So you cannot make a weapon out of spent, no matter what you do with it, out of spent nuclear fuel from a commercial reactor. That's what people get upset about, because they think you can make a weapon out of spent fuel, and you cannot. Okay, you just can't. Now, some of the molten salt reactors actually separate. It's not solid fuel; it's actually liquid fuel, and you can separate the plutonium easier. But still, there are ways to make it non-proliferable. So anyway, so a weapons reactor like we had out here, we had 9 of them out here at Hanford site, and Chernobyl was a weapons reactor. People don't remember that. It was designed to produce a ton of plutonium. That's why it was graphite moderated. And the North Koreans have weapons reactor, of course, 2 of them. So this is how you make a bomb. You need a weapons reactor, not a commercial reactor. You need to leave the fuel in only 6 months, not 6 years. And it's a completely different thing. Now, there's 2 types of waste here. When you split 235 or plutonium-239, you get these fission products. Now, most of the fission products are either not radioactive at all, okay, like gadolinium, or they're really, really hot. Okay, so they have, and if you're really hot, that means your half-life is very short, because you're really hot, you're disintegrating like crazy. So if your half-life is 8 days, like iodine-131, then the rule of thumb is 7 half-lives to background. So 8 days, 56 days, 2 months. 2 months and iodine-131 is completely gone, right? And there are fission products that have half-lives of seconds or minutes, months. So that's why we take the fuel out after 6 years and put it in a pool of water for 5 years. All of the hot stuff is gone in 5 years, except strontium-90 and cesium-137, because they have 30-year half-lives. And so again, rule of thumb, 7 half-lives to background. So after 210 years, let's call it 300 years, they're gone too. So after 300 years, all of the hot stuff is gone from spent fuel. Gone. All the gamma emitters that are hot. Now, this stuff is not very hot. You can hold plutonium-239 in your hand. It's not going to hurt you. It's very weakly radioactive, and it's an alpha, so it can't even pass your skin. You have to powder it and breathe it in order to get any real dose. Okay. The same thing with neptunium and americium. They're just not, they're alpha, and they have longer half-lives. Now, there's a couple of fission products or activation products like technetium-99, which is hot. It has a 400-year half-life, but it's a beta, and it's not very energetic. So again, you have the really hot stuff and then the not so hot stuff. So if you just put it aside in dry cask storage or storage for 200 years, it's cooled off almost completely, and then you have this long-lived stuff that makes the fuel, the spent fuel, basically as hot as the ore it came from. All right, so people talk about this being really hot for 50,000 years. It's like, no, it's really hot for 200 years. Then it's not so hot for 50,000 years. So when you're looking for a repository, you need to think about these 2 types, these 2 categories or partners, I guess, in the waste: the really hot short-lived stuff, and then the not so hot long-lived stuff. Now, if you want to make a bomb like we did up here, you take your weapon reactor fuel after 6 months, you remove the cladding, and you dissolve it up in acid, and then you put it through a series of steps to extract and purify the plutonium. Now, the reason you want plutonium is because it's it's more efficient at fissioning, all right, than uranium-235. So you don't need as much. It's very light. Okay, so if you're going to missileize a weapon, you want to put on a missile, you want plutonium, period. Or if you're going to graduate to thermonuclear weapons, hydrogen bombs, you need a plutonium trigger. All right, so you want plutonium. That's the only reason you want plutonium. Little boy that we dropped on Hiroshima was a uranium-235. All you need to do is enrich it. So Iran took that route. North Korea took the plutonium route. So during this processing, the first 2 steps basically gets rid of most of the junk. Okay, most of the fission products, most of the hot stuff, right? So cesium and strontium. So that goes into the high-level tanks. Now, the high-level waste tanks are defined not by the amount of activity, not by how hot it is, but by where it came from. So it came from these two processes, so it's high-level waste, even though it may not be high level. I mean, it may not be high active. And now, then these polishing steps, though the waste from that goes into the transuranic waste tanks, the true tanks. And there's about 150 of these and 20 of these, right? Now, the funny thing about the high-level waste is that since we started all of this, since the 1970s, most of the cesium, strontium is gone. We removed half of it to control heat in the tanks, and the other's been through 2 decay lives. So most of the tanks now, almost all the tanks, are true or low-level waste. There's no high-level waste left at Hanford. Okay, that should sink in there. There's no high-level waste left at Hanford, except barcode still says high-level waste. Okay, bureaucratically, administratively, it's still high-level waste because it came from these 2 steps, even though it's not hot anymore. So, whoops. So of the 57 million gallons at Hanford, you could convince yourself that maybe 600,000 are high-level waste, and 56.4 million gallons are now true or low-level waste, most of it low-level. Now that should, you'd think that should change the way you treat this waste if it's not high-level anymore, right? Because you only vitrify high-level waste. No one in their right mind would vitrify low-level or transuranic waste, right? Well, Washington State would, so that's you know, so we're still going on with this nonsense with the vitrification, even though it's not high-level waste, which is very, very interesting. And we'll talk about that more. So that's waste. Okay, 1957, the year I was born. The predecessor to DOE and NRC, the Atomic Energy Commission, AEC, approached NAS in 1955, actually, and said, you know, we've been making some of this weird waste. We've been making bombs for, you know, over 10 years, and we just, you know, started up the first nuclear reactor at Shippingport. You know, we're going to have some weird waste here. What should we do with it? And that's natural. You go to the National Academy of Sciences if you want this kind of question answered. And they came back relatively quickly, and it was an easy decision because there is nothing like the Permian salts, okay? These salts, it takes 1 billion years for water to move an inch. So if you want to isolate anything for 1 billion years, then it doesn't matter what the waste is or how hot it is, or short-lived, long-lived, doesn't matter. It's gone for 1 billion years except uranium itself. So, you know, yeah, you put it Permian salt, of course. And then even better is at a half-mile depth, it's somewhat plastic. So it will encapsulate and crush the waste and then come to a steady state that, again, it takes 1 billion years for water to move an inch. Now, there's 10,000 square miles of the best waste, which is near Carlsbad, the Delaware subbasin. 10,000 square miles, 6,000 feet deep. And the top 2,000 are especially pure sodium chloride, which is what you want, and especially perfect for this. And that's where WIPP is. We have a nuclear waste repository that almost no one knows about, which I will talk about in detail. So this was an easy decision. I mean, even, you know, geochemists like me, geologists, they're probably a half hour around the lunch table said, of course, Permian salt. We all agree, right? Yeah, right. That's it. 30 minutes for anyone with any knowledge of this to come up with the right rock. This is the best rock in the world for nuclear waste disposal, or for anything you want to get rid of forever and ever. So this was not a difficult decision because scientifically it's a slam dunk. Now, then things got weird in the 70s. They got political. So the AEC establishes these new categories. Oh, by the way, this repository was designed and built for everything, for all 4 categories. At that time, there weren't categories. It was just, you know, radioactive waste. Then, you know, AEC establishes these 4 categories that I talked about. And then we formed the EPA. And then 76 comes along, and we put reprocessing of spent fuel on hold. Now, everyone talks about Carter making it, you know, illegal, but he didn't. He just put it on hold, and then Reagan reversed that in 1981. So it is not illegal or even wrong at all legally to reprocess spent fuel. Reagan made that just fine. Then but the first, and then DOE was formed. So DOE and NRC split from AEC. So the first DOE secretary, Jim Schlesinger, who was a great economist, he was not a scientist. And the weapons guys had his ear. So basically someone said, you know, we might want to get this stuff back out of the ground. So we're going to spend billions of dollars putting it a half mile below the earth in an incredibly permanent repository, and you want to get it out of the ground later? I mean, are you crazy? This isn't Walmart. You know, this isn't a department store with a revolving door. Okay, if you want to get something back out, don't throw it away to begin with. Okay, but that kind of didn't sit with anyone. So the idea, okay, we're going to have a retrievable repository for the high-level waste and the spent fuel. A retrievable repository. Now, by definition, the salt is not really retrievable, although that's a red herring. You could retrieve it easier than putting it in another lousy rock. But still, because the salt collapses, the thought was, okay, well, we won't put it there. Okay, we're going to find a hard rock that will stay open for 50 or 100 years so we can retrieve this stuff later if we want to. That was the beginning of the end for our nuclear waste disposal program. Now, because no one knows what the hell true is, true continued on into the salt. Okay, so, you know, no one even thought twice about it. And then 1982, the Nuclear Waste Policy Act. Now, here's, you know, the graphs of this waste. Again, you know, after 1970, the high-level waste all became true or low-level waste, with only a teeny bit of high-level waste left. So you'd think that would make a difference. Now, the Nuclear Waste Policy, the Nuclear Waste Policy Act called for 2 repositories, not 1, 2. One was on the East Coast and one was on the West Coast, okay? And there were 17 candidate sites, all right? So there was some in the, you know, South and West, and then some in the North and East. Now, the powerful Eastern politician said, no way in hell is it coming to the East. Okay, so, and at that time, even they outmuscled the West, the Western politicians. So the idea, you know, killed salt as a host rock, and by 1987, the candidate sites were narrowed down from 17 to 3, and those 3 were Yucca Mountain, Nevada, Hanford, Washington, and Deaf Smith County, Texas. Now, who was Speaker of the House in 1987? I remember it well. Jim Wright from Texas. Okay. Who was House Majority Leader? Tom Foley from Washington. And there was this new junior named Harry Reid, who'd just been elected. And they said, they just pointed to Harry and said, Harry, it's yours. That was it. That was the decision for Yucca Mountain. So, of course, as karma goes, Harry Reid, you know, became Senate Majority Leader. Okay, and he spent his entire career fighting Yucca Mountain. And in fact, after 1987, in fact, the day Yucca Mountain was picked in 1987, I remember, I think it was in August. I was actually at Yucca Mountain because I'd been working there for 2 years already. And the next day, the Las Vegas newspaper said the headline was the Screw Nevada Bill. And from that day on, the 1987 Nuclear Waste Policy Act amendment was called the Screw Nevada Bill because that's what it was. And you couldn't get elected dog catcher in Vegas if you were for Yucca Mountain. So from that point on, it was doomed anyway. But it was a political decision, and it didn't sit well with Harry Reid. And the bad thing is that Harry Reid became very powerful, and he killed a lot of nuclear stuff, not just Yucca Mountain. Now, in 2008, Reid told Obama, you're going to kill Yucca Mountain, right? Or you won't get my help in the Senate. And Obama did. And I was so happy that he did. And everyone cried foul. Oh, is killed because of politics. Well, it was born because of politics. Born and died from politics. So it didn't really make any difference that way. Yucca Mountain's a lousy rock. In fact, what makes a good deep geologic nuclear waste repository? Well, there are 7 criteria that we have always used to evaluate the suitability of a site for a deep geologic nuclear repository. And if we look at Yucca Mountain, Yucca Mountain is a highly fractured, oxidized, variably saturated dual porosity hydrologic system that sits on the edge of the Las Vegas shear zone. Now, which of those words give you confidence, okay, in this rock? Okay, it is a lousy rock. I spent 25 years trying to make a lousy rock work. All of us did. Very proud of the work we did. It was brilliant, brilliant science, all right, just to show that this is a crappy rock and that you need to re-engineer it so much that the cost goes astronomical because it's a lousy rock. And so that's okay. I get it. So the first criteria is you want a simple hydrogeology, right? You want to know what's going, you want it not so complicated, you don't know what the hell's going on and where the water's going, right? So, okay, well, Yucca Mountain, no, that's a bad one. Okay, a simple geologic history. No, it's very complicated there. A tectonically interpretable area. I'll give it that. Yep, we know what's going on. It's on the edge of the Mojave Block that is being rotated by the Garlock Fault on the north and the San Andreas Fault on the south. Okay, it's rotating the Mojave Block around and around, and that's what the Las Vegas shear zone is on the edge of. You don't want to put a nuclear waste repository there. That's dumb. Okay, so is nope, the isolation is not robustly assured for all waste types. It should not matter. If the rock's doing what's supposed to be, it should not matter what the waste form is, right? Shouldn't matter whether it's grout or glass or, you know, sludge or whatever. It should not matter. But it does. That's why we're vitrifying. We're vitrifying only because we chose Yucca Mountain. Because Yucca Mountain is such a lousy rock that we decided we had to vitrify it and then encase it in a super copper canister alloy that's going to last 10,000 years. It's like, what? I mean, I love the pyramids. Pyramids are great, but we don't make things that last 10,000 years. So if you're going to depend on the performance of this repository on human-made engineered barriers, we had to make 7 of them, then you're in the wrong rock. And that's no question about that. No, we minimal reliance on engineered barriers. No, we actually are completely relying on engineered barriers at Yucca Mountain because the rock doesn't do anything. Performance is independent of the canister. Nope, you only should have to make a canister that meets Department of Transportation requirements to get it on the road or on the rail and get it to the repository. Once it's in the repository, you shouldn't have to depend on the canister lasting at all. I mean, that just means your rock isn't doing anything. So, okay, we'll get that. Now this is interesting. I'll grant, you know, Yucca Mountain this. We call this the Walmart effect. There has to be a Walmart within an hour's drive or no one will work there. I'm not kidding. This is, we can talk about it, sufficient social, political, and economic infrastructure. No, there has to be a Walmart and a church and a school. There has to be something where people can live that's less than an hour away from the site. Otherwise, you will never get your workforce to live there for years, right? So that's an interesting thing. And of course, Pahrump is about 45 minutes away, just like Carlsbad is 45 minutes away from Wick. Okay, so as a result, to fully implement the Yucca Mountain repository would cost well over 300 billion, and now it's up to like 600 billion. To put the repository in the correct rock only cost about 30 billion. If you do the right rock, it's cheap, easy, and fast. All right, because it's the right rock. If you choose the wrong rock, well, now you're going to re-engineer around the fact that you picked the wrong rock. So here's Yucca Mountain, the engineered barriers. You know, when I was a barriers guy for a while, and I came up with the richest barrier, but you know, they settled on titanium drip shields. Titanium drip shields? Are you crazy? I mean, first of all, the titanium alone is going to cost you 80 billion. And second, have you ever tried to form titanium into corrugated? I mean, if you ever work with titanium, it is strong, but it is brittle. And it's really hard to work with. This is the most expensive material to work with, engineering-wise. So yeah, this was dumb. That's when I stopped working on Yucca Mountain. So, but unknown to most, transuranic waste continued on into the salt as planned, leading to the waste isolation pilot plant. Now, here is the surface facility. It's been operating for 24 years without a hitch. I mean, there was one problem in 2014, but it wasn't WIP's fault. It was someone put wrong stuff in the drum up at Los Alamos. I could have killed the guy. He used to work in my old group. Just really mad. So anyway, so And if you look here, this is really hot stuff being transported via a 72B cast, just the kind of cast we use for spent fuel over any other weapons reactor, weapons material, anything else. So we know how to do this. It's a piece of cake. Now, again, this was only permitted for transuranic waste, the definition of which is greater than 100 nanocuries per gram of plutonium-239 equivalent, up to 23 curies per liter. And that number comes from reprocessing spent fuel. But WIPP was originally designed and built to handle everything. It was only narrowly, narrowed down to transuranic waste politically in the 1970s. Now, 16 square miles of the 10,000 square mile deposit was set aside in the 1992 Land Withdrawal Act, about 45 minutes from Carlsbad. And when WIPP is full, it will only use about a square mile or so. That's it. And transuranic waste is volumetrically greater than all the other waste put together. I mean, spent fuel on high level. So, this is a piece of cake. We know how to do this. This is what it looks like. There's 4 shafts into the underground. It's 2,150 feet below the surface. There are the horizontal drifts, which are horizontal boreholes. It's a mining terminology. And then there are these panels. Each room, there's 7 rooms in a panel, and each room is 300 feet long, 30 feet wide, and 13 feet tall. And it can hold 12,055 drum equivalents. So this is a lot of stuff. And we are almost full. We are filling panel 7, okay? And we're cutting panel 8. Now, why is this salt even here? Well, 270 million years ago in the Permian, the Proto-Pacific was off the coast of Utah and Arizona. There was a little arm of the Proto-Pacific Ocean that came up into West Texas and southeast New Mexico, and the whole continent was tilting. This is a time of recession. That's why all the Permian salt deposits of the world are so extensive. And so what happened was this arm kept getting shut off tectonically from the ocean, and it would dry up, and then it would reflood and then dry, evaporate, dry, evaporate, dry, evaporate over 60 million years, and precipitated, 30 million years, it precipitated 6,000 feet of salt, the top 2,000 being particularly good. Now, if you look in the WIPP salt, and I'm sorry I'm not there with a huge hunk that I always carry around when I give talks like this, if you hold it up to the light, you can see a little square crystallographically trapped 270 million year old seawater. Hasn't moved an inch, hasn't moved a millimeter in 270 million years. And we recently extracted DNA from it. And it's viable, actually. Cellular material from cell walls and dried granulated bacterial husks. This is halophilic bacteria. It's no big deal. It lives in brine. It's the only thing that can live in brine, and it hasn't changed much in the last 500 million years. But it's a testament to how isolating this rock is, because biomolecules don't last 270 million years. They degrade relatively quickly. So they either degrade thermolytically, because you bury the rock, so the temperature gets up above 81 degrees, 41 degrees C, which is the denaturing point of DNA and proteins, enzymes. That's why you do not want to have a temperature. You don't want to get a 109-degree temperature, because your DNA starts unwinding and you die. So what happens, it's a really nasty thing. So when you get to be 105-degree fever, that's when everyone starts putting you in ice baths. Okay, but this rock never was buried deep enough to exceed 41 degrees C. So these were not thermolytically degraded. This is pure salt, so there's no naturally occurring uranium or thorium that occurs in almost everything except this salt. And so it wasn't radiolytically degraded. It was buried fast enough, but not too deep, but fast enough to remove it from most cosmic rays. So again, nothing has happened to this rock in 270 million years. And it hasn't even, no faulting, no folding, no volcanism. It hasn't even tilted 1 degree in 270 million years. And as a geologist, that is rare. Okay, you couldn't manufacture a rock this good. You couldn't dream of a rock this good. And it just there for us to use. So it's a soft rock geologically, it's not a granite. So, but if I threw a chunk at your head, it would hurt, but it's not strong, very strong. So you don't have to blast or anything else. You just take these big, they're called Marriott continuous miners, and they have carbon tungstide teeth, and you just drill it and you just dig it out. It's easy, very easy. No blasting, no one ever gets hurt. So in 2000, we started in 1999 with the first shipment of transuranic waste. Most of it not so hot, but there is some high activity waste in transuranics. And so in 2007, we started shipping the really hot stuff. I mean, this is no different than shipping high level waste. We know how to do this. We've been doing this for 20 years. This is like no big deal. This is what it looks like if you're down 2,150 feet below the surface, which I used to take people down all the time. Took Jim Clyburn down. Took the Blue Ribbon Commission down. Always, loved, and everyone would come up and go, "Oh my God, this is great!" And they'd say, and Jim Clyburn said, "Why isn't everything here?" And I said, "Well, that's your job. that's not our job. We have the solution. If you want to use it, you got it. But we can't lead you to salt and eat it." So, so this is what it looks like. This is one of those rooms. So this is all pure salt, sodium chloride. This is all the stuff that doesn't have much cesium and strontium in it. All right, it's just plutonium, uranium, neptunium, and americium. So you just need a 1/4-inch mile steel. These are 55-gallon drums. 7 of them are called a 7-pack. That's shrink wrapped together. These are standard waste boxes from Los Alamos. This is a 10-drum overpack, so you can get some pretty big stuff in there if you chop it up, and that's fine. Now the really hot stuff is in the wall here. Okay, it's robotically dug out a 14-foot hole, and then robotically push these shielded cans into it, and then plug it with a 4-foot metal wrap cement plug. So this guy standing here is getting 1/10 of the radiation dose that we're all getting sitting here listening to this. Because he's a half mile below the Earth, so there's not much cosmic rays getting down there. This is all really well shielded. This is natural salt, so there's no naturally occurring radioactive material like there is in the uranium in the walls beside you. And this is well sealed. So the biggest dose this guy's getting is from potato chips he ate for lunch. I mean, as you know, potato chips are the most radioactive food, right? Potato chips, yeah. Potassium 40. It's funny. Not enough to hurt you, of course, but enough to be interesting. So after 24 years of operation, we have disposed of more waste that was ever destined for Yucca Mountain to begin with. And the equivalent of 750,000 55-gallon drum equivalents, 22 storage sites cleaned up. Rocky Flats is in WIP. That's why Rocky Flats is a greenfield. And then, whoops. Yeah, what am I doing? And then I got something in the way of this. No one's contaminated, no one's died. There was one event, the little bit of americium leaked out because, again, someone put the wrong stuff in the drum and it popped its top, but no one was contaminated. It was no big deal. DOE freaked out, the state of New Mexico freaked out, and they spent 3 years and $500 million when we had a plan for 3 months and $30 million, and it would have been fine. But nope, you gotta go big. Okay, so that's nuclear waste. That's WIP. Now, Hanford, the weird stuff. I'm going to say right up, this may sound weird, but Hanford tank waste poses no threat to human health and the environment. None whatsoever. None. Off-site. The only risk that's posed is to human workers on site because they handle the waste. So there is a slight risk there. And the risk is greater if we vitrify it, which is kind of weird because it triples the volume of waste. And, there's nothing like, pouring 15-ton molten ingots of radioactive waste. Okay, so it's like, yeah, there's a little bit of danger there, but even though no one's going to die, most likely. But yeah, there's no risk off-site. There is no mechanism to get any of this waste out of Hanford. even if you walk away from this, and I'll talk about this, and you let the stuff all leak out, don't do anything to it, by the time it gets to the river's edge, which is where it all ends up, it's only 4 millirem a year, and that's in the year 5,000. 4 millirem a year is nothing. I mean, that's one cross-country flight from Seattle to DC. So, what's the problem here? I mean, I love it when I hear people say this is the most dangerous place on earth. It's like, no one's ever died there. Okay, no one's ever been, no one's ever gotten cancer from working there unless it's asbestos and beryllium. And it poses no real threat off-site. So how can you call it the most dangerous place on earth? Well, because we've been calling it that for years, so it just kind of sunk in. Here's what the tanks look like. The bizarre thing of these are 500,000 to 1 million gallon tanks. The weird thing is that we set up these tanks so that we could fill one and it would overflow into the next one and overflow into the next one. So we don't really know or didn't know what is in each tank because they're all different. Okay, and it depended on where in the process you were getting the waste. So as you can imagine, the first tank, all the heavy stuff would drop to the bottom, and then it would go off, go into the next tank, and it would be a completely different composition. So back to this. So again, we would start filling these tanks, and then we'd let it overflow and overflow. We basically had them in 3 tank units. And by the time 1990 came around, we didn't know what the hell was in any of these tanks. I mean, we knew generally what was in them and generally what the total would be, but we didn't know what each individual tank was. Okay, so we get that. Okay, now, the regulatory limit on doing anything, disposing of anything, cleaning up anything, is that you cannot exceed 4 millirem per year in the closest down gradient water. Okay, so at the river's edge at Hanford, you cannot exceed at any time in history, in the next 100,000 years, cannot exceed 4 millirem a year. Here is a simplified version of the subsurface geology at Hanford. This is a very complicated geology, okay, very complicated. But all of the vadose zone is the unsaturated zone. So the water table is down here. So all of the water table is right here. All of the stuff that ends up at the river goes into the water table and ends up at the edge of the Columbia River. Now, these are the kind of models we use to predict what's going to happen. And I'm not going to go into this, but I did a lot of this in the 90s. I was the one that actually measured the properties of each of those rocks with respect to every type of water content, with respect to every type of constituent, every type of radioactive species. This is a complicated model, all right? But we got very good at them, just like we're getting very good at climate change models, okay? So if you get the right input, you can get a reasonably confident result. So what that all ended up in is the environmental impact statement. So whenever you do anything like this, you have to have an environmental impact statement, right? Whenever you do anything that will affect the environment as a whole. So, and you always have to have a no action scenario. And the no action scenario is you walk away from this. You do nothing. You absolutely do nothing. Maybe you put a wrecker cap on it. Maybe you fill the tanks with sand or something so no one falls in, but you walk away from this without treating it. Then all of the alternatives were different types of vitrification with different types of closure. And the reason it only is vitrification and not grout, which it should be, is that DOE does not make law. Congress makes law, and Congress made this law that Yucca Mountain would be the repository and that you would vitrify this waste. And so, so the hands were tied basically. Now, if you look at all these alternatives, these actually are the results, and they're really good. I won't talk about the core zone boundary is the edge of the 200 area, where the tanks are sitting, the edge of that area. You really care about the Columbia River because that's the regulatory driver. Okay, so no action. You walk away from this site, you do nothing. In the year 4978, 5,000, the dose, the maximum dose, the peak dose of the river's edge, and that's if you're in with a straw right next to the sand. Once it gets into the river, it's gone. So you can't even measure it. So, but right at the sand It's 4.37 millirem a year. Now, the regulatory limit is 4. Now, does anyone believe 3 significant digits? Raise your hand if you believe that this model is good to 3 significant digits. No, of course not. This is 4 plus or minus 2, right? This is 1. This is 1, 1, 1, 1. All of these alternatives, however you vitrify, comes out to be about 1. And that 1 is from what has already leaked out. You can't get better than that. And why would you care? It's 1 millirem. And where the background here is 620 millirem. The background in Seattle is 600 millirem. So what are we caring about 1 for, or 4 for that matter? Now, the funny thing is that 4.37, in order to do anything, or by law to do anything, you have to exceed 4. So, this exceeds 4. That's funny. Very interesting. Now, 4 millirem per year is right up there with, again, 1 round trip, coast to coast flight, watching an old color TV. God, don't sleep with anyone. My God, that's terrible. So, this is absurd. This is so low, it's absurd. And just rocks and soil would give you 4 times that. In fact, if you move to Spokane from the west side, you'll get an additional 50 millirem. Now, I know we should make it illegal to move to Spokane. I understand that. But, this is nonsense. Now, if you just grout it, this 2R it didn't come from DOE, it came from a bunch of us. You get the same result. All you're doing here is removing the source term. So it's not leaking out, it's a solid. And solids dissolve very slowly, especially if you have a cap on them and you're in a desert. Okay, so, this is, all you have to do is grout these in place, or just take them out of the, tank side, grout them and chip them someplace else, whatever. You don't need to vitrify. It costs 10 times to vitrify. And it doesn't get you anything. There's no better performance here. Vitrification versus grout. And the no action, you really don't even need to do anything, almost. Okay, but no one's going to accept that. I get that. So we talk about alternatives. The current plan is vitrification. And the chemistry of this waste is incompatible with glass. Now that should tell you right away that vitrification is not really the thing you want to do, because it's the wrong chemistry. So there are many technical hurdles still left. It's going to cost just to vitrify over $160 billion over 60 years. It triples the volume of waste. And since most is low-level waste, vitrifying low-level waste is never done in the world, ever. No one is stupid enough to vitrify low-level waste. This is insane. Also, it takes about 43,000 gallons of diesel per day to run these. And it'll double the carbon footprint of the site. Now, if you grout this, and we have great grout formulations, I did a couple, they work as well or better than glass. The waste chemistry is very compatible with grout. It likes to be in grout. There are no technical hurdles. We've done this umpteen times. It would cost $50 billion over 30 years. It does not increase the volume of waste much, and grouting is a standard method for true waste and low-level waste. There's no additional fuel needle, little effect on anything, on the environment, nothing. It just saves you a ton of money, and it's easier to do. So why wouldn't you do that? The state of Washington does not want to grout. They hate the word grout. Not sure where that came from. Okay, so what are the costs of regulating radiation doses to such levels? If you raised the regulatory level from 4 millirem to 100 millirem, which is still 6 times less than background, you would save $400 billion, and you could do this really fast. It's like, what does it do? What do you get out of having such a low dose as your regulatory limit? Well, I'm sorry. The better question is, how much do we consider the value of a human life to be? Well, EPA says the value of a human life is $7 million. Now, I wish I was worth $7 million. I'd kill myself and give my family $7 million. And so it's so when EPA comes up with these numbers about values and human life, they use a value of $7 million. So if someone dies in a toxic waste spill, that's what the value of that is. Now, the healthcare profession considers $316,000 to be the average value of a human life because that's the average paid out in healthcare over a lifetime in America. This is the average. Now, the legal, legals, they have it right. This is the average historic legal value in wrongful death suits. Now, if you're, a celebrity, you'll get more. If you're Joe, Joe on the street, you'll get less. But that's the average historic payout in wrongful death suits. Now, this is horrible. This is the death benefit to families of deceased soldiers. So this really tells you what we value in this society. Now, you can get more in certain combat death situations, but that's the average death benefit. Now, if you're a young male and I chop you up and sell you on the black market, I can get $45 million. Now, that's value. That's real value. Now, if you're DOE, we are spending $2.5 billion per life saved in the year 5000 because of this regulatory limit. We don't, and that's a theoretical life. No one will die from 4 milligram a year. No one will be even affected by it since background is 600. So here's $2.5 billion that we spend on a theoretical life that we're saving in the year 5000. 5000. Anyone think that's reasonable use of that money? Now, we could use that one life saved to immunize the entire continent of Africa against the 3 biggest scourges, and we could save 25 million people as opposed to that one theoretical life. So this is an ethical question. This isn't a scientific question or a political question. It's an ethical question. What the hell are we doing? Wasting $2 billion a year up in Hanford doing nothing. Now, the other thing about vitrification is it will take an annual budget at Hanford of $9 billion to carry out vitrification. Do you think Congress is going to give Hanford another $7 billion a year? I don't think so. In fact, Congress has said, no way, you do it with what you got. So if you put it in the salt, we don't need any money from Congress. It's already paid for. Okay, the nuclear waste fund's already paid for it. So we can do this if we put it in salt. If we don't put it in salt, we can't pay for it. Another interesting conundrum. Now, separate from high-level waste or bomb waste or whatever, interim storage of commercial spent fuel. It's ideal, it turns out, it's 160 years. So these casks are rated for 160 years. They're licensed just like nuclear power plants every 40 years. I mean, for the first 40 years, and then you have to relicense every 20 years after that, just like a nuclear power plant. But these are overbuilt. I mean, these are over-designed like crazy. And they just sit there on cement pad with some guards and a gate. I mean, this is the cheapest thing you could do. And they will cool off over 100 years until we decide to burn them in fast reactors, and it'll be easier to use because it'll be cooler. It'll have gone through 3 decay lives of strontium and cesium. So, I mean, this is brilliant. It's wonderful. Just set it aside. You don't have to worry about this. This is where everything is at now, of course, at all of the nuclear reactor sites. And it's just fine there. Now, you've heard of deep borehole disposal. I like this for some things, okay? When you're down 4 or 5 kilometers into the crust, there is no mechanism to get it back out. Absolutely no mechanism to get this back out, as long as you don't put it in the middle of a volcano. But, so this is permanent disposal. You don't have to do anything to it. Now, the problem is you have to drill a hole 4 to 5 kilometers deep. Now, the oil industry, we can do that. That's a piece of cake. 8 inches wide. But if you're going to do whole fuel assemblies that are pretty wide, that's going to be tough to drill that deep and expensive. But the new modular reactors are perfect for this. Like the pebbles, you could just, you can make the disposal canister any size you want, any diameter you want, and just fill it with pebbles and just make it long and thin. Or salt, molten salt reactor waste. You can put it in whatever shape container you want. Okay, so again, this is good for some things. And even high-level waste, bomb waste, you could just put it in long, thin containers instead of, short, fat ones. So this is good. I like it because it's cheap, it's easy, and everyone can have their own waste disposal site, which scares everyone, right? It's kind of funny. So here's where we're at. This is it. This is the only outcomes we have. So either defense waste, you either redefine it as true and low level and send it to WIP or to another salt repository, which is still going to be cheap, or to something like waste control specialists. We have low level waste disposal sites. We have 4 of them around the country, and that's what they're designed and built for this type of waste. So we can do that. If we don't redefine it, then it's going to stay right where it is, unless we, expand WIP. Commercial nuclear fuel, you put in interim storage, and then eventually you dispose of it someplace. Either in WIP or elsewhere, or in another salt repository, or you put it to fast reactors and burn it to get 10 times the amount of energy out of the same fuel, 10 times less waste. And that waste will all be fission products, all short-lived. So if it's not going to last more than 300 years hot, then it'll become low-level waste after that. So again, you can put it in low-level waste sites or put it in borehole sites, because that waste you can manage to whatever shape you want. But that's it. This is our only choice. South Dakota is not going to raise its hand and say, we'll take it. Really, either everything stays right where it is, or we expand WIP as it was originally intended to take everything. And New Mexico does not want that. And every time you talk about that, they say, you lied. You told us only transuranic. It's like, no. We told you everything. You decided as a state that it was only going to be transuranic. So don't put that on us. That's not us. Thank you.
Well, I got to thank you, Jim. That was fantastic. So I won't be able to take that sort of picture of everybody. Really, really fantastic talk. We've got a couple questions.
Yeah.
And I'd like to ask Betty. You asked a number of questions on the chat, Betty. Did you get your questions answered by the presentation? Or...
I just was a little confused. Jim had made the comment several times about there's no high-level waste at Hanford tanks.
Right.
When did that become that way?
So that gets back to this. Let's see. Let me
because when I worked there on the tanks program, there was high-level waste. So what changed?
Was it before? Yeah. So did you work on it before 1990?
No.
So there was no high-level waste there. The thing is, it's still called high-level waste. Bureaucratically, administratively, it's called high-level waste because it came out of these 2 processes. But it's no longer high activity because most of the season.
Okay, so that was what confusing me. Are you talking about high activity or high level waste, which has a specific legal definition as the first cycle raffinate of spent fuel dissolution, right? Right. For bombs, not commercial, right.
So it started out as high level waste.
There is that type of thing in the Hanford tanks.
Right, but it's no longer hot.
But it's no longer hot, but it's still high level waste.
Right, it's still bureaucratically, it's still called high level waste.
Okay, well, so if you were confusing me because you were kind of changing that term around. So there is legally still high level waste there. Right. So DOE has been trying to redefine it.
Right.
Now, that was going on when I was working on the program.
Yeah. Right. So they're trying. They've tried to use DOE Order 435.1. I think it is, and they should be able to redefine it as to what it is, because there isn't anything over 1 curie per liter left in any of these tanks, and we have stuff. We have stuff that's 13 curies per liter in WIP. Okay.
Yeah, it's kind of like this imaginary classification.
Right.
And it's the same stuff. It's just because it came out of this thing instead of this thing, it's defined as something else.
Right. Which is,
it doesn't make sense.
Right. And it's fine on
So-
paper
so-
in 1957. Okay. But
So would
when
it be fair?
what?
Would it be fair? Would it be fair then to differentiate high activity versus high level? And
Yeah.
what you're saying is there's no longer any high activity waste in Hanford.
Right.
There is a classification of high level waste, but it's not highly active anymore.
Right.
Okay.
So there
You
is
just confused me because you were using the two
Right,
different
right,
things,
right,
and I
right.
thought there'd been some kind of decision that there's no longer any.
Well, there has,
other
I actually wrote a paper on this for the DOE lawyers in 2011, and I should probably send it to you. That
Oh, okay.
the
well, that's
funny,
after I left. So
right, and NRC refused to define high level waste in terms of activity. They refused to. In fact, they said a stupid thing. They said you'll know it when you see it. It's like, oh my God. And that reminded me of Scalia's, you'll know porn when you see it kind of thing. Remember that? It was like, oh God, give me a break. So, but there is a limit, and that limit is 7 curies per liter for cesium-137 and 4 curies per liter. No, sorry, 7 curies per liter for strontium-90 and 4 curies per liter for cesium-137. And there isn't anything over a curie left per liter in any of the Hanford tanks. So there's, by any stretch of science, there's no high level waste left in those tanks.
high activity.
That's good.
Right.
So did that cover your question, Betty?
That did. I just got confused because of Jim's terminology.
Right. There's legal space, and then there's science space, and then there's regulatory space, and they all don't really agree very well.
I thought a miracle had occurred since I left.
And then a miracle occurs.
Right.
So I've got 2 quick questions for you, Jim. The first is, are the intermediate solid nuclear fuel tanks potentially susceptible to terrorist bombing? Could terrorists go in there and set some bombs and create a dirty bomb out of that?
They would make a mess, but it wouldn't go very far. I mean, they could contaminate Hanford. That's all they would do, contaminate Hanford. But yeah, there's no way it would do anything else. I mean, I love it that everyone in Seattle and Portland is scared of stuff coming down the river. There's no mechanism to get any of this to the river. The only way this could get over there is if I actually went into the tank with a shovel, drove over there and threw it on someone's head. I mean, that's the only way you can get any of this stuff over there. There's no atmospheric mechanism. There's no riverine mechanism. There's no groundwater mechanism to get any of this out at all, to even to Richland here, right south of Hanford, 10 miles south. Nothing. By the time it gets to the river, like I said, it's 4 milligram a year in the year of 5,000. So,
Let me ask one other. It seems like what you're saying is that for the U.S. to increase its nuclear power footprint, to expand our nuclear power footprint significantly, it boils down to a political solution on what to do with the waste. Scientifically, we know what to do with the waste, but politically, getting it down to whips or boreholing, or even Yucca Mountain, if we wanted to spend that money. Right. We know how to take care of the waste. As far as our plants are concerned, all it would be is a solid nuclear fuel, which we would store on the plant. So it just boils down to the low-level waste. Is that burying the addressing the long-term storage of the low-level waste? And that's a political solution.
Well, I mean, the bomb waste, right? Weapons waste is a whole other thing. How we deal with that has nothing to do.
I'm not talking about bomb waste. We're talking about nuclear power plants in the U.S. They would produce solid nuclear fuel and they would produce low-level waste. the solid nuclear fuel, we'd put in the isolation tanks,
Yep,
the
right,
intermediate
dry
tanks like we're talking about. And
Okay, now what
potentially
is
we
the,
could reuse that.
what's the low level waste from commercial reactors?
I'm sorry?
What's the low level waste from commercial reactors? There really isn't any low level waste from commercial reactors.
Oh, I thought you had said before that the commercial reactors produce the two things. They produce the low level waste and the solid fuel waste. You're saying all they produce really is the solid
Yeah,
fuel
solid
waste?
fuel. Now, some of the new designs, like the molten salt designs, are not solid fuel, they're molten fuel. Okay. And so you can strip that out and put it into containers and then dispose it however you want to in salt or borehole. But yeah, but most of what we consider as commercial waste is solid, fuel rods. Yeah, and so you
But
put
there are
those,
some designs.
right. Yeah, so you put
Some
those
designs.
aside in dry cask storage, and we will burn those in fast reactors in the future. I mean, there's no, it's too valuable a thing. But we should have a centralized storage facility, and we want to build one right next to WIP, because when we do burn that waste from that will eventually go into WIP. And so we should have a facility near WIP that stores the high level waste, the spent fuel, and also facilities next to it that can reprocess it into new fuel and get the stuff out for medical purposes and do all sorts of nuclear things with this waste, which is quite valuable. And then eventually that should go into WIP. I mean, we only need one repository. We don't have enough waste, and never will have enough waste in 1,000 years to warrant more than one repository.
Okay, good. And you say there's no low level waste, even on some of the nuclear design, like the sodium?
Not really. I mean, occasionally, you could have some building waste, like construction waste that's mildly contaminated, during construction or something like that. But it's very minor. And we have repositories for those. Low level waste, we have 4 repositories in America. 5, Utah, US Ecology up here at Hanford, Andrews, Texas, waste control specialist, and Barnes, South Carolina.
So to summarize what you just said, we could basically expand our nuclear power plant footprint in the U.S. and we know what to do with the spent nuclear fuel, the solid waste. You just put it in the containers near the plant. And basically we could get by with that.
Oh yeah, no problem. It's very stable, the thing about these dry cask storage, even if you have it in it for 160 years and the concrete starts cracking, just put it in a new container. I mean, it's not really that big of a deal.
Okay. No, that's really good news. So the bottom line being that we don't need to solve the problem of where we store the waste fuel for nuclear power plants. We've got a solution for that.
Yeah, we got a solution to that. But it all hinges on it hinges on New Mexico. Stopping this nonsense that, I mean, they're the solution. This is the best rock in the world. Why would you force us to go to a crappy rock someplace else? It's like, wait a second.
But we don't have any waste. For most nuclear plants, you wouldn't have any waste that needs to go there, right? Not now.
Not at first, yeah. But eventually you're going to have some waste that eventually has to get disposed of. And WIP is the way to do it.
But in the near term, building up our nuclear footprint, we're okay, and we should work on politically the long term. And the ideal solution is the salt or boreholing.
Right.
Okay.
But
I
think, this subject is so complex in the process of trying to sell this publicly. There needs to be distilled a discussion that is understandable.
Well, I guess,
and not scary.
Right. I guess the best way to put it is, we know how to do this. We know what to do it. We know where to put it. We know how much it's going to cost. It's really quite easy. We've been doing it for some waste for 20 years without a problem. No one has ever been harmed by nuclear waste, not killed, harmed. No one has ever been harmed by nuclear waste at all. It's the safest thing you can do is handle nuclear waste. I'm safer than working at McDonald's. I'm safer than working at Walmart. And so it's safer to handle nuclear waste than to cross a street in Albuquerque or in Seattle. And so, we kill 5,000 people a year crossing the street.
And certainly safer than driving a potato chip truck.
Right.
Okay.
Yeah.
All right.
Yeah, I think this is the critical question, really, because when we talked about how, as CCL, can we play a part
Right.
in convincing the public? And this is the critical question that we have to answer and give people a sense that they can believe this, it makes sense, and it exists. You know what I mean? It's not just some double step that people are trying to do.
Think about how I could cut this talk down.
Oh, yeah.
It's kind of hard, though, because you got to, the nuclear primer at the beginning is kind of important.
It is.
And
that's something I'd be happy to help you with.
Good.
Because I do a lot of presentations on things. I've done presentations on this topic at a much different level,
right.
At disposal of waste and whatnot. And, I have some ideas. So
good.
I've got a Jim, I don't know if you're open to it, but I've got a couple of, I worked in instructor training and special assignment in the Navy. And one of the things they said as a basic rule is tell people what you're going to tell them, and then tell them what you told them. And so, and that was for sailors, and so you really had to get through to them. And so what I was thinking in this is, a little bit of here's the topics we're gonna go through, and at the end of it, here are the takeaways. And
right,
especially for CCL, where are the areas where we can help?
Right.
Education, what sort of lobbying, what sort of issues does the populace need to understand, and then Congress. And so I would be glad to help with that, but this has been a fantastic presentation for me. And I know the people that were here were able to attend, got a lot out of it. And I really want to thank you very much. But before I sign off, can we make sure that everybody's got their questions answered? And also, Jim, are you willing for a little bit of a follow-on discussion, say with Betty and myself and anybody else wanted to
I'm yours.
Have a little.
I am yours.
Okay, you are us. Jim Bloss has a question, real quick. Hey, Jim.
Yes.
Very good.
Yeah, I'm sorry. Yeah, got to get myself together here. So, I forgot what my question's going to be. I'm terribly sorry.
Marjorie had a question too.
Yeah, go ahead.
And Lee has a question.
Oh, I remember, but
and I have a question when you get a chance.
Marjorie, you're muted. If you had a question.
I didn't. I just want to echo the fact that, it needs to be consolidated and said over and over and over again to those people on the west side that might be, just not viewing it, or they just don't have the information.
Right.
So I just think this was so good, both of these sessions. And I'm going to tell everybody I can and pass on the videos, both on YouTube or through Facebook or whatever. But I think it's so important. And thank you so much, Jim. I really.
You're welcome. You're welcome. Lee.
So, Jim Bloss, let's go back to you real quick if you're ready.
Yeah, I was just going to make a comment. Working up a presentation where people will eventually feel comfortable with the concepts is one thing. The real issue, isn't it the fact that there's a bias, an anti-nuclear bias, and it's just ingrained to the point where I don't know what you can do about that.
No, the only thing you can do is say, hey, listen, no one's ever been hurt by nuclear waste, and we've been doing this for years, and it's a piece of cake. So where's all the bodies? I mean, I always say that no matter what, talking about nuclear, I say, where's all the bodies? It's like, you know, no one ever dies from radiation in America. No one ever dies.
I like it coming from you. You know, if you have a politician telling you this stuff, you wouldn't believe it anyway.
Right.
But you know, given it's you and even you know, it's taken a while for us to trust you, Jim. You're a smart guy.
I'm just a shill for the industry.
You're a smart guy, but you talk fast. So
Well, that's why this is recorded and there's a PowerPoint, and I'll be putting out those links so everybody can review this. And there'll be text as well. So one more question from Lee, and then I think we've got to wrap things up.
Well, and Don had a question too, but Lee, go ahead.
Oh, does Don have a question? I don't see his hand. Okay. Oh, there it is. All right.
Lee.
The CCL, when they really get on something, they like the carbon pricing, they tend to respond to hundreds of experts that are credible in an organization. Like 3,500 economists have signed on to a letter of support for the carbon pricing. I think it's some number, but my desire is that we pour on the gas a little bit with CCL support of modern nuclear solutions to decarbonization. And I wonder, Jim, having one Jim that is totally trusted is different than having an organization, nationwide organization of 100 or 1,000 Jims signing on to a letter.
So there's two answers to that. There are two organizations, the American Nuclear Society, just like the American Chemical Society, American Geological Society, whatever, you know, they're the society of academicians, right? That every science area has. So that's ANS, and then HPS, the Health Physics Society. They're the ones charged with radiation protection and safety. And both of those are totally on board with this. I mean, they love it. So, and I know them both well. And so if we get something by them, and they've already written stuff on.
There's already an organization, Physicians for Social Responsibility, and their nationwide chairman, I believe, is Mark Vossler, the chapter leader for the Kirkland CCL.
I'm sorry, don't get me started on the Physicians for Social Irresponsibility. Highly unethical, just absolutely highly unethical. And the women that started that, I can't tell you how unethical they are. It's just terrible.
Do you see any pathway to one of those two organizations you're mentioning, creating some sort of a joint letter advisory to CCL?
Absolutely.
And what would be the 2 or 3 main points of the letter? Would it be buy-in to SMR, buy-in to in New Mexico?
It would be the safety record of nuclear power. It has the best safety record of any source of energy, period. Then the future, the new advanced reactors, how they're even safer than I don't know how you can be safer than no one ever dies, on a nuclear power plant, but hey, we can be safer than that, right? So yeah, they can talk about how the new ones can't melt down, and that's good too. So yeah, we could go through those points.
Has there been
So-
any
so we-
National Academy of Sciences positions taken on this?
Not really. They've not wanted to. I mean, again, you can go back to 1957 National Academy of Sciences, and they said salt was the best rock you could have. So you can always do that. But the new one is very neutral. They've purposely been neutral on nuclear. But you know, there's they like it. I mean, they understand how useful it is. They're always dragged in by DOE or NRC to do some study.
So, good. So we're going to have a follow-on discussion.
And then of
I'd
course,
like to-
wait,
I'm sorry,
hold-
John.
wait. The
Don had a question.
The IPCC has come out very strongly for nuclear. They basically say you can't do this. You can't decarbonize without nuclear. Jim Hansen and
Yes.
you know, all the leading climate scientists wrote a letter to the last to COP26, I think it was. And so you
Right.
know, we can
So
have
that would be sort of similar to the Economist statement in the Wall
Right.
Street Journal
right,
on carbon pricing.
right. Good.
Yeah. So Don, real quick, could we get your question? And then I
Oh,
wanted to
Sure.
close
So
this off.
there's still, you know, those of us who live in the Tri-Cities have all that fear, uncertainty, and doubt because all the stories that we've seen in the last 20 years, you know, the plumes, the bubbling tanks that explode with hydrogen, you know, these are, I know, inflated, even radioactive tumbleweeds, you know, these become national stories and people still remember them, right?
Right.
Now, I'm pretty sure that the radioactive tumbleweeds was some health physicist who turned the sensitivity of his instrument all the way up and just was looking for one click on his little thing and found one somewhere. But you know, these major things, the plumes, the bubbling tanks, you know, these I think a lot of people need to get past this in order to look at these Xenon 100
again,
reactors.
Right. And the way to look at that is every
And
single
even
thing that
McCluskey,
Right.
McCluskey never died, you know?
Right. Yeah.
So
So that's what you do. You say, okay, we get all these things that always come out because everyone sensationalizes anything that happens in nuclear. But whoever dies, no one ever dies from that.
but
And
how do you
can
fight it
point-
other than no one ever dies? You know,
Yeah,
I
but
mean,
you
do you
look at
grab
every other industry. I mean, you look at every other industry. We have chlorine trucks that go through cities and blow up and kill people every other year. I mean,
So,
you know, people
do we
die.
hold a handful of these little graphene pellets, you know, like this and say, hey, everybody, look, this is safe, or something like that, you know? I mean, because
Yeah, and we've done that. And unfortunately, the anti-nukes are very numerous and very well funded, and just on there continuously. I mean, there's just two new books out that are wrong. I mean, two new, one by Sierra Club and one by a very famous anti-nuke scientist, Alvarez.
Well, but
And-
also the hot stuff, you know, people are probably concerned about that. Not just the uranium, but like you know, what was in the McCluskey room, Americium-241, and you know, that's 430-year half-life. So people are going to be looking at that small fraction, that's that 430 years, and go, oh, that's all a whole bunch of waste.
But these weren't nuclear power production.
No, they weren't. But
These
people
were
conflate those
plutonium
things.
refinement
Right.
accidents.
We
and
need to
love
just
bites.
separate those.
nuclear waste and nuclear bombs have nothing to do with each other. You don't even use the
Right.
same reactors.
Hello again. Thank you for watching this very informative talk. I cut off the Q&A at the end there with Jim's important and emphatic note that bomb waste and nuclear power waste have nothing to do with each other. The important distinction being that we are only interested in nuclear power waste. And the audience spent the next 20 minutes or so both reinforcing this point and discussing our thoughts about how best to get this important information out to the rest of CCL and the U.S. citizenship. This was something I felt wasn't pertinent to Jim's basic message about nuclear waste. Also, A few days after this talk, an article came out about some highly radioactive waste at Hanford, and I thought it would be a good idea to see if Jim would be willing to talk a little bit about this, which he was. What follows is that discussion. Everybody, this is a post nuclear waste meeting addendum, and it has to do with a article that recently came out about building 324 and the high contamination there. And Jim was kind enough to come back on and give a response to that. So Jim, would you care to say anything about that?
Good. Yeah, we had been talking about nuclear waste, and nuclear waste is a separate issue. Then there's just contamination. Now, there's lots of contamination around the world. I mean, industrial contamination, some radioactive contamination, and Hanford is one of those places. I mean, the Manhattan Project, in order to build the bomb and then do a bunch of research on bigger bombs, we carried out a bunch of research in different buildings, separate from building the bomb and creating nuclear waste associated with that. We actually just did a bunch of research, and some of those buildings, like building 324 in the 300 area at Hanford, I actually used to work in the late 1980s, became contaminated. And when you're now demolishing those buildings, and then you dig up the floor and do monitoring, you say, oh my God, this is a little bit more contaminated than we thought. Okay, so that's fine. And contamination is just contamination. The risk is what you care about. How risky is this to the environment, to human health, and that kind of thing? And it's not much of a risk at all. I mean, Hanford, the radiation at Hanford has never killed anyone or even harmed anyone. Now, asbestos and beryllium and mercury and lead, those actually hurt people and kill people. But the cancer rates at Hanford, of the Hanford workers, the 100,000 plus Hanford workers that worked over the last 70 years, the cancer mortality rates are the same or less than the general population, which is odd, except that we're very good at seeing radiation, measuring it, monitoring it, and protecting against it. So it has never really had any horrible effect that people think of when, this as soon as you say radiation. So the 324 building, I mean, it's contaminated. We are cleaning it up. We need to clean it up, of course, but it's not going to hurt anyone. The risk to anyone outside of Hanford is minuscule, about the same risk as being hit by a meteorite. There's really not any measurable risk. I mean, it's 1 in a billion, 1 in a trillion. These numbers are so ridiculously low that you should not worry about them. All right. Now, the word radiation makes everyone worried suddenly about everything. And so it's like, okay, but you need to put it in perspective. You need to understand risk and dangers. Now, the Hanford site, the tank waste, everything else, those have a small risk to the people working there, but they have no risk to anyone out off-site, anyone in Seattle or Portland or even Richland right next door to it. There's no risk to those populations because there's no mechanism to get this out. The groundwater, once it moves through, eventually it'll get to the river. The concentrations when it gets in the river are minuscule, well below background. So, the airborne things just don't move that far. So it's very, very hard to get this stuff off of the site. But at the same time, you need to clean it up. So we are cleaning it up. Now, that building, when you demolish these and you get more information about what's underneath them, then you adjust to do that. And that's all the 324 building is. We adjusted, well, this is a bit more contaminated than we thought, so we need to rethink how we're going to deal with it. And that's fine. Now, the really hot stuff that we talk about is gamma emissions from cesium-137 and strontium-90. Now, those have half-lives of 30 years, or the rule of thumb is 7 half-lives to background, so 7 times 30, 210 years. So say by 300 years, the hot stuff is going to be gone. And all you're left with is very low-level stuff. So again, it's not like this is contaminated for thousands and thousands of years with really hot stuff. It isn't. The hot stuff goes away very quickly because it's hot. So again, if the nucleus is disintegrating really fast, it's really hot, that means it's going to be gone soon. So the radioactivity, the hotness, I guess you could call it, is inversely proportional to the half-life. So if something is really disintegrating fast, then it's going to be hot, but it's going to be gone. So that's one of these kind of weirdly ameliorating issues, is that the hotter something is, the shorter it is, the shorter the life is, and the less you have to worry about it well into the future.
Excellent. Excellent. Well, thank you for coming back and explaining that, Jim. And
You're welcome.
I very much appreciate it, and I learned a lot. Even though I had a good background, and I have a good background in nuclear science, decent background, not
Good.
not nearly
Yeah,
as
no,
good,
very
but a
decent.
decent background experience.
But this is
And,
weird.
so
This
very-
is right. This is weird stuff. Who knows this stuff? I mean, there's
Yeah.
only a relative
Yeah.
handful of us, because I have been in this for 40 years, so I better know
Yeah.
something.
Yeah, and of course, scientists have been discouraged from talking about this stuff because it
Right.
supposedly will scare the public. But yeah, now it's time for us all to learn
Yeah.
about it and learn how safely it can be handled, and what the risks are and what the past shows about those risks. So this is great information. Thank you very much for coming back, and thank you for the previous presentation as well. It's great stuff, great information.
You're welcome.
Thank you, Jim.
Good stuff.
Okay.
Bye.